first, we construct, so I'll call this F. The set of edges of F will be simply the modular group itself. And the vertices will come in two kinds. Vertices, and I'll call this type of vertices. They are simply the cosets of the subgroup generated by S. So these can be written as M times S, where M is from the modular group. And if you are here to be even more explicit, so this subgroup contains only two elements, right? This is S and identity. So this is simply identity S times M. So here we are talking about the set M and S. So any vertex of this type of the graph is a pair like this. Okay, and there's another vertex type, and they are defined to be the cosets of the subgroup generated by L, or the inverse of L, it doesn't matter, it's the same group. So this is M times L, such that M is from the modular group. And again, if you need to be more explicit, I can write that this is M times identity L, L squared, which is just the set M, ML, M, L squared. So now that I know the edges and the vertices of my graph, I must define the incidence so that it becomes a graph. And the incidence is given as follows. If an edge is incident to a vertex, V, and the union of this I'm going to call Vf simply, if and only if that edge belongs to that vertex. So vertices are just sets, they are just cosets, and edges are just elements of the modular group. So this is a well-defined incidence relation. And for example, what does this say? This pair says that M, since the edge M belongs to this vertex, this edge is incident to this vertex. And there's another edge which is incident to this vertex, which is this one. So this pair also suggests that in the graph we have an edge like this. So we have an edge called M, which is incident to this. MS. And there's another one, of course. There's another one which is incident to this vertex. It is simply MS. Okay? And this one says me that in the graph I have pieces like this. So I have a vertex which is called vertex M, ML, ML squared. And the edges are called M, ML. Oh, okay, this must be ML, this must be ML squared, so that L is left when we go up. So we have some convention for drawing them. Okay, this is our graph. So why is this a tree? Why is this a tree? Because, well, by definition, it must be a connected graph without any cycles. Okay? So it is connected because it is generated by the elements S and L. Okay. And it is acyclic, that is, it contains no cycles because it is freely generated by the elements. Because there are no relations in this presentation. So F is a tree connected dessins S and L generate the group, and acyclic since they freely generate. It is bipartite. F is bipartite for the simple reason that two classes are either disjoint or equal. So here is a subgroup of the group, and the vertices are its conjugates classes, its cosets. And those cosets are either disjoint or either they are equal. And this is the reason why you will never have an edge like this. You'll never have a situation like this, because then these two classes, these two cosets, must have a non-empty intersection, which should be the edge joining them, which cannot happen because these are cosets of subgroups. And the same thing for this. For vertices of this type of degree 3, they are never neighbors, so neighbors of the vertex of this type are always this kind and so on. So this is a bipartite tree. Why we have chosen it to be a bipartite tree? Because we want this group to act freely on the set of edges. Okay. Simply, we arrange this so that we arrange this simply by choosing the set of edges of the group of the graph to be the elements of the group. Simply.
Maybe can you explain briefly how do you prove one? Is it a free product? Right. But all the difficulty now is in one shifted to one.
Yes. How do I prove it? I just take a word. In S and L.
Yes.
I take a word in S and L.
You have to show it's not reduced to zero identity if it's not L.
Yes, and you show that there are no relations between.
Yeah, how do you do that?
It is purely algebraic. I must think about it, okay?
But is it not nicer to first do 2 and then do 1 by using the section on the tree?
Yeah.
But then how are you going to construct the action on the tree?
So for example, you can take the fundamental domain of the action on the upper half plane and can take the borders as the tree vector.
Yes, but then you're using too many things. Here we started from 2,500 years ago, okay? I don't want to use highly developed, sophisticated technology. I will do that right now.
Yeah, but you already picked on all these.
Okay, so
you method to prove that the group is free.
Yeah, those days they didn't know what the groups. But, so how come they can know about free groups? Okay, so let me admit that I checked. In fact, I asked one of my students to do it once, but now I forgot. I have to think about how to do it more easily. Now, everything is perfect, so that the PSR2, the group, acts on F. Well, there's one more thing that I have to say, that this is not simply a graph, it has an extra structure, the structure of a ribbon graph. And how? Because I have the vertex of degree 2 doesn't matter, but vertex of degree 3 can be oriented in this way, canonically oriented. So the orientation would be L square L and ML square N. So this is a permutation. So for each vertex, I have a canonical permutation, cyclic permutation of the edges which are joined at that vertex. And that is the definition of a ribbon graph. And this orientation can be given by a drawing. So you can imagine that all these orientations are coherently given by a drawing. So the modular group acts on F and it preserves the ribbon graph structure. It doesn't change.
So for those, well, you have other kind of vertices too. Or what's the orientation for that? They have vertices.
It doesn't matter. So it is a cyclic order and it doesn't matter which one you choose because they are not the same thing.
So you just fix one.
1, 2 or 2, 1. So you just forget about it.
Okay.
Okay, how does it act? Well, on sets, on the set of edges, it is simply by multiplication from left. So I take an element, let's say W. W will send edges to edges. Well, it will simply send the edge labeled M to the edge labeled W times M. So on the level of the edges, this is simply the left regular action of the modular group on itself. Okay. Okay, so it sends, M sends vertices of this type to vertices of this type exactly in the same manner. So if you have a coset, well, it should be W, right? W. So if I have a coset M times S, that coset will be sent to W times M times S. And if I have coset concerning the action on the other elements, so this ML is sent to W times M times L. So here this action is free and transitive. Because it is just a left regular action, but here it is not so. It is transitive, but it is not free. Why is it not free? For the simple reason that M S M minus 1 sends this coset to itself. Okay, just multiply and you end up with the same thing. Why? Because if I repeat, this will cancel out, but I'll have an S here. So I'll have S times S, but S is from the subgroup. So if I multiply, I get the same thing. So this is simply M times S. So this action fixes all vertices, all vertices of this type have a non-child stabilizer, and that stabilizer is simply the subgroup generated by this element, and this subgroup is simply a subgroup of order 2. Okay, so this is conjugate to S, so it's of order 2. So this subgroup fixes that edge, and it is of order 2. I then for vertices of this type. So here I'll have M times L, M minus 1. If W equals this, then this will fix the subgroup. If I put L square, it will be simply the square of this element. So the subgroup, which is generated by M minus 1, will fix this order. So this is a very nice action of a group on a tree indeed. Now, what is interesting here is that any subgroup of the modular group also acts. Okay, since the modular group acts on tree F, any subgroup of the modular also acts. And we can quotient the graph. This action is nice enough. This action is nice enough. It is by ribbon graph automorphisms, so that you can since it's different transit on the set of edges, you can quotient by the action of a subgroup and get something decent. If you have an arbitrary subgroup of an automorphism of a tree group, if you quotient the tree by that subgroup, it will be some very bad orbifold. But here the situation is not so. It will be orbifold in some cases, but a nice one, and in many of the cases it will not be an orbifold. So let gamma be a subgroup. So gamma acts on F, again exactly in the same manner, and we have a quotient graph. The quotient graph of this F over gamma, the quotient. Graph. So if I have to be more precise, I must define its edges and its vertices. The edges are gamma orbits of the edges, which is just the cosets of gamma, right? And the vertices are simply gamma orbits of vertices. The incidence relation is also easy, and it is easily found, but it's a little delicate. We'll discover it in a slightly different way. But anyway, these graphs, they do need a name, okay? F over gamma. So we call them modular graphs. I think it is natural naming. So we call these graphs modular graphs. But there are many alternative names in the literature. I mean, for example, any dessin is a kind of modular graph. You may hear them under the name cyclic cubic graph, cuboid graph, trivalent ribbon graphs. Some instances are called Jacobi diagrams. There are also some dual notions. There are also some dual notions such as triangulations, dosage tilings, and so on. There are many words in the literature which refers to the same thing or something which is not very different from this modular graphs. I don't know. I think that these ones, they merit a name, and we coined the name modular graph. Okay. And these are also ribbon graphs. The action preserves the ribbon structure, and these are so F over gamma modular graphs are bipartite ribbon graphs such that vertices of this type are of degree always 1 or 2. Of this type are always 1 or 3. I mean, a subgroup may send the edges coming out of a vertex over themselves, okay? A subgroup may stand this one, this one to this one, this one to this one. And in the quotient graph, we are going to have an edge like this. Otherwise, it is going to be a traveling graph. Okay? This is the first thing. By the way, these are dessins, huh? These are some special descent d'enfance. But from the point of view of arithmetic, in fact, they include the general case in a certain sense. And I hope I'll have some time to explain that too. This is the basic fact. And you might ask, how do they look like? To see this, let us start by the simplest case or hardest case, whatever. So the group itself acts transitively on the set of edges, so there will be only one edge in the quotient graph. So it will look like this. So it will be only one edge with two vertices incident to the vector edge. In general, this is a very special example, and in general, I'm going to have something like this. So some surface with some punctures. So, and I will explain where does the surface comes from, and I'm going to have some graph. I don't know. So there will be only vertices of degree 3 or 2. So these are those of degree 3 and these are degree 2. We may have things like this. Something like this. So I'm not sure if I have drawn enough arcs. But it will look like this. So a modular graph is something which looks like this. And now I'll explain how and why. So,
but you consider only finite motions, or
whatever.
So non-compact surfaces also.
Yes, it is possible. We can consider, and Ayberk. That's what Ayberk does, in fact.
Mm-hmm.
That's what he did. He considered subgroups generated by one single hyperbolic element. They are very small subgroups, so that the quotients will be big. So they turn out to be annuli. So annuli are big quotients, okay? So this is any modular graph. I don't say it can be embedded. I say is embedded. Canonical. On algebraic curve. Or a Riemann surface, if you prefer this description, whose structure is determined by the graph itself. And this embedding is a particular one, so it will have some punctures, and this embedding is such that the puncture surface retracts to the graph. It is not an arbitrary embedding. Okay, now I come to your suggestion. Okay, now we can do that. This is another fact. The tree has, again, a quite canonical realization. And it is not just topological, but an analytical one. Analytical realization. So we just take the usual well-known action acts on the upper half plane, again by Möbius transformations, the matrix signing PQ are S to Z plus Q or Z plus S. And we have the usual fundamental domain, which looks like this. So you know, you have this picture, but there's a little detail here that one part of this arc belongs to the fundamental domain, the other doesn't, right? So you take just one piece of this arc. This arc, and then you take its orbit. If you take its orbit will look like this. It will look like this. And so in fact, it will be isomorphic to 3. In fact, I can do this identification without passing through this hyperbolic geometry, but this is the most easy to do, so I'm doing it this way. So two things, because since I have chosen this to be the orbit of some arc, the actions are compatible. The action of the modular group on the upper half plane and the action on the tree, the realization of the tree, are compatible, because F is here, the realization is simply the orbit of just one arc. And then I can quotient them simultaneously. And what do we get? If I do this, I'll get that F over gamma embeds on H over gamma. And H over gamma is a Riemann surface. Ah, I'm done? No, I started at least 10 minutes before, after.
No?
No? No, yes, I'm sure. It was 5 past.
We are running.
Huh?
You are only 2 minutes late.
No, here, it was at least 5 minutes. Anyway, okay. How much time do I have then?
Well, I would say we're over, but 2 more minutes if you like.
Okay, 2 minutes. Then I must be quick. Here's the option. Now if I do everything, then what do I get? I mean the quotient, if this is PSL to Z, then I'm going to have some arc, right? As I have drawn. And what is the embedding? Here I'm going to have the modular group, which is something which looks like this. Probably most of you know the picture. And this arc is just this arc. By the way, I think that this arc also merits a name, so let's call it the modular arc. And what do we have? And here we have a puncture. So now here, what is this? What I have here is now F over the whole group, and here I have H over the whole group. And we have the usual diagram from topology. Usual diagram from topology. This is a covering of this, a graph covering of this, and this is a graph covering of this. And if you lift, if we call this phi, and if we call this I, then phi inverse I is just F over gamma. So I have just described the modular graphs as quotients of the tree, okay, by subgroups. Now I suggest another description. I suggest the description that they are the lifts of this modular interval to coverings. It amounts to the same thing. And now if you take this arc, let us call this T, and if you call this, if you lift this to T, then you are going to have something in H over T, right? H over gamma. Okay. Now, so by lifting this, you obtain driven graphs, modular graphs. And by lifting this, you obtain triangulations. Okay? And this is the usual dual graph construction. If you wonder how to do this and how to pass on the modular graph to the triangulation on the surface, it is very simple. If your triangulation is something that which looks like this on the surface, then you just construct a dual like this. And so on. And in this way, we can claim that a triangulation of a surface is nothing but a subgroup of the modular group, up to conjugacy. Okay, that's all.
Is it clear that on the board above you said that the graph you obtained by just taking the whole orbit of our half arc
Yes.
is the same as the modular graph we defined before?
Yes.
Yes. Is it obvious?
I mean, we define it so that this holds. Okay. So analytically, I mean, on the topological level, it's very clear, right? We have something and you just quotient and we have space. So the question is how to express all this in terms of graphs. We express this in terms of graphs so that this is true. This is it. But I expect one more question.
Okay, I have a question.
If you don't ask, I'll ask.
This your triangulation, you only triangulate the very special surfaces. Right? This is a upper space quotient by arithmetic subgroup. So you're not talking about a general triangulation of surfaces. I mean, like you just lift the fundamental domain of the modular curve to get the ideal
I mean, as I said, this is the simplest way to express this correspondence. I don't need any machinery at all. I can express everything on topological level. So I have some topological level, I have some triangulation of it, and so on. So ideal triangulation.
I mean, you only get a certain ideal triangulation, but what you said earlier is that
I get all ideal triangulations.
all ideal triangulations.
Yes, every single one of them. If you have a topological surface,
Yes.
every single triangulation of that topological surface comes from a subgroup of the modular group.
How? How does it work?
You have to
This
find
way.
the covering.
Huh?
The triangle. If you have the triangulation, you have the cover.
You take the dual graph,
I see.
and the dual graph, you can see it this way. The dual graph is some graph, right?
Yeah.
You can look at this universal cover. It is just F.
Yeah.
So this is just a quotient of by that.
But my question is that the dual graph is a tree, you know, the covering tree. Why
Yes.
is this all necessary F? You can have many trees. It's necessary F. It's not obvious.
These are only one equivalent for number.
Oh, but yeah, so you have to impose some condition on ideal triangulation in order to have something about the tree.
I mean, I think you're confusing something between analytical category and topological category. No?
Maybe we'll talk about it later. Okay.
But, okay, one more. So if you don't ask that question, I'll ask the question. What if you lift? You can lift this, you can lift this, or you can lift this arc.
I see. Actual energy. I see. So it's ideal triangle.
So this was a duality between graphs, right? So you have a triangulation and you have a dual graph. So we see that in fact there's a triality here, not just duality, but the triality. So what is, my question is, what is the trial of a triangulation?
Yeah, F is
The trial graph of a triangulation. Just try to find it out. Thank you.